So Fran, when we talk about structural parts, and obviously that's a big part of what powdered metal is all about, especially in the case of gears as an example. What become some of the limitations that we have with powdered metal when it comes to maybe gears or other types of components? Where do you see the limitations of today's powdered metal?
Well, if you think about, where powdered metal is right now, as you say, it's great for shape making. And, you look at a classic example of a gear like this. And the one advantage PM offers, as you well know, I mean, put the powder in, you get an exact shape out. You also get things like this unique keyway that's put in there, which comes along with it. But if you look at parts in general, or structural parts in general, there's a couple of things people are that may be generally interested in. One would be strength. Think about the strength of the tooth of the gear.
Right.
So it's rolling against something. The last thing you want to do is have a tooth get knocked off. It kind of wipes out the whole transmission in that instance. Fatigue. It's a similar thing in that this is not a static part. It's always being engaged with something else. So you have the fatigue issues as well. So you have a lot of different key characteristics that you want to look at, and also hardness. Let us not forget hardness, because you don't want a soft gear, because it's certainly going to deform and wear out. So I think when you look at it in the perspective of what are the key characteristics, we listed 3 of them. And a key thing is, if the part's being made today, we see that if it's being made today, it's a good opportunity. And what opportunities for improvement might you have? Well, if it's being done, as I said, probably best to leave it alone. But if it's facing a redesign where people are saying, well, now I suddenly want to up that performance and things of that nature, how can we make it better? And behind us we see a chart that we've worked on and kind of developed that, we talked earlier about how sintering is still in the 20th century and some of the other aspects are now 21st century. And if you look behind, you can see where 80% of the parts fall into a fairly narrow, relatively low strength range. I think as we go forward and as we look at newer applications, people are going to want to up their performance, be it weight, be it perhaps other things that they're looking for. So I think what we need to look at is how can we take a part and make it better, make it stronger. And certainly with advanced compaction, advanced sintering, and now even ultra-high temp sintering, we have that opportunity to take it to performance levels people hadn't seen before. And
let me back you up. You threw out a couple of words there. Advanced compaction. What do we mean when we talk about advanced compaction?
With advanced compaction, we always talked about, I'm always reminded of the Muppets cartoon and the Swedish chef. You put the powder in the mold and you bring the head down. Well, in a sense, that's powdered metal at its best. And what we do is we say, okay, we still put the powder in the mold. So, take this gear, for example. You have a mold that's the mirror image of this. So you put the powder in. And most compaction is done with standard lubricants and, without doing any special things to the powder or to the tooling per se. With advanced compaction, now suddenly a little bit of heat goes a long way with the right combination of lubricants. So whereas if you were compacting this, maybe you could get to again, come back to our density criteria. You see that, maybe 7.0 was the max we could achieve. With the advanced compaction technology, maybe you can get to 7.3. So it doesn't sound like a big difference, but you may see a 50% improvement in the parts performance. And it's through innovative uses of dyes and tooling and powders, certainly, that allow us to get there. And being practitioners of that art, we do have that capability of getting to those higher densities and higher performance levels without a lot of major issues, per se.
Okay. So the compaction portion, we've established that we can improve the performance there through advanced compaction, increasing density.
Yes.
Now you talked about high temperature and ultra high temperature sintering. So what are we talking about there? And how does that begin to play into this?
Now right now with the current materials, you have the ability of, most people currently are using copper steels. In the PM industry currently, over 50% of the parts are made with basic copper steels. Well, they work okay, but Are they going to be the future? Again, we talk about this transition now into the next generation or into the next century. And I think the copper steels per se have worked, but we're going to reach a limit to what they can do. And I think that limit's quickly approaching us, if you will.
Yes.
So now what we can do is, if we start introducing alloy steels, or we want to talk about maybe putting a little nickel in. Nickel's very good for increasing the toughness of the part. You know, and if you think about a transmission, and we talked about Corvettes earlier, and you want a lay rubber coming away from the stop plate. Well, suddenly now your gears better be able to withstand that initial shock load, or again, you're going to have transmission pieces flying out of the bottom of the car, which is never a good thing, I might add. Having blown a transmission or two in my life. But anyway, having said all that, so now if we can increase the toughness of the part, but when you put things like nickel in there, and even copper, which has been the bulk of what people have done in the industry, it diffuses a little bit, but it doesn't fuse all the way. So you only get partial benefits of those alloying additions in the part. Now with high temperature sintering, and even with ultra high temperature sintering, you get a more homogeneous distribution of those alloying elements that you put in. Plus, it opens the door to more unique alloys that we can put in as well.
New elements.
New
that we can
elements,
use.
yes, exactly. You know, forgive my metallurgical jargon, you know, you go right to a certain thing. But anyway, new alloying elements that you can add that can increase the strength, increase the hardness, give you better overall performance. And the other crazy thing is, since PM parts have holes in them, what you really want to do with that is the holes are just nature of the process, but you want to make sure the holes are nice and small and nice and round. So what ultra high temperature sintering and high temperature sintering does is round that porosity, which now, instead of having a needle-like crack sitting there, it's a nice round crack, so you don't have stress risers and things of that being generated internally into the parts. So we could spend all day talking about this, but it does create a lot of interesting opportunities, from alloying, advanced performance, how we can get a more homogeneous structure, and as well as, you know, what you can do with the porosity to improve the overall performance as well.
So again, this idea of taking powder metal bringing powder metal into the 21st century. I think your chart here, am I correct in saying, if I'm looking at this chart, really what it is you're trying to say here is, today, with these technologies that we've been able to develop, we're able to compete with other metal forming technologies that we've never been able to compete with in the past, and be able to offer our customers significant cost reductions along with these types of products.
Yes.
Fair statement?
Yes, and this particular chart behind us is that it was actually developed for gears, believe it or not. And we borrowed it from the gear producers to say that, depending on the type of gear you have, if you have a low strength gear, well, maybe you want to use like a phosphor bronze type steel. Or if you have other applications, well, maybe a cast iron gear works. But as you talk about automotive transmission gears now, you're suddenly thinking about something that's very highly stressed, very highly loaded. You know, and the last thing you want to do is walk home because of the gear failing. So now you want this higher performance level. And as we talked about before, it's not just sintering, but it's materials. It's how you process the part. So you want to definitely put everything out there that you can. And as we show, I mean, you know, as you move up the ladder, the requirements get harder and harder, and you need all the tricks of the trade to get there.
You bring up a good point too. What about like even the shape making aspect of it? Are there benefits within gear tooth design per se, that because of PM's inherent shape making capability, that can further enhance these, even the things that we're looking at here?
Yes, there is, but even if you take a minor step backwards, you know, here's a classic example of a gear for an angle grinder. And think about it, well, they'd have to start out with a piece of bar, machine all this away, and then come in and cut your teeth this way. Well, with powder, you simply pour the powder in the die, you close the die, you come out with a net shaped gear.
We're back to the Swedish meatballs.
Yeah, back to the Swedish meatball concept.